Miguel has devised a method to measure how long a bouncing ball is. Okay, I'm going to tell you right now. Bouncing ball and contact time. This word contact time and bouncing ball. Right away as an IB teacher, I look at this. I don't even need to read or turn the page further. My thought right away is this has got to be impulse and momentum. I cannot think of a single other thing that they would have me study in this problem. And so what I'm going to do is grab my data booklet and I'm going to write down every single thing related to momentum and impulse that I can, even before I read further. And I'm back, having aggressively grabbed my data booklet. I open it frantically to the page. Actually, not really, kind of calmly. So here we go. Here's the formulas. I'm going to write them all down, useful or not. P is mv. F is delta P over delta T. Impulse is F delta T, which is delta P. Now here's the one they don't give us that I'm going to use. F delta T equals mv minus mu. That's one that I memorized by taking this formula and putting it with this one. So, we get some heights, we get some maximum scale readings, very cute. Let me just see if there's anything else I can get some immediate feedback on. Aha, we've got force and time. So one small thing here is, let's just remember when we get an F versus T graph, let's remember the area is the impulse, which is also the change in momentum. Just want to kind of get that out there. All right, so here we go. Calculate the speed of the ball when it strikes the pan. And we're dropping it from this height to which the ball bounces, maximum reading on the scale. So an idea that I have here is I'm probably going to want to grab this equation here. V squared is u squared plus 2as, where a here is going to be g, which is 10 meters per second squared. And I'll use that probably for both of these. So let's go ahead. It says the speed of the ball when it strikes the scale of pan. So v squared equals u squared plus 2gs. V squared is, it starts at a speed of 0 squared, so v squared equals 0 squared plus 2 times 10 times the 0.8 that it falls. When I actually saw that, I'm going to get v is 4 meters per second. By the way, I did do that in my head just now. 2 times 10 is 20 times 0.8. 0.8 of 20 is going to be 16, or 2 times 8 is 1.6 times 10 is 16. And the speed of the ball when it leaves the scale pan, we're going to say this, v squared is u squared plus 2 times 10 times, and it only returns to a height of 0.6. And we got v squared is, 0 squared at the top is u squared plus 2 times 10 times 0.6. We're going to use absolute values here because clearly we can't get square root of a negative number. So 2 times 10 is 20 times 0.6 is 2 is the square root of 12. So when we actually work out the square root of 12, let's just see. It's going to give us about 3.5 meters per second. So the change in momentum, and let's be clear. So we're going this way at 4 meters per second, and we'll actually say that's negative, and then we bounce back up at 3.5 meters per second. So the change in momentum, please remember that down means negative sign. Okay, that's something I see a lot on our written work that we need to kind of be aware of as we're working through these problems. So the change in momentum is going to be mv minus mu. And in this case, that's we get a mass of 0.2, so 0.2 times 3.5 minus 0.2 times negative 4, so that's 0.2 times 7.5, and that ends up being 1.5 Newton seconds as the total change in momentum. Awesome. Now here, what does the area under the graph represent? We already got it. The area is the impulse, or the change in momentum. Now, from the previous problem, we actually got that the impulse is 1.5 Newton seconds. So to get the contact time, let's be clear. 1.5 Newton seconds is going to be 1/2 base times the height of the triangle. Well, the height is 50, and the base is delta t. So we're going to end up getting 3 equals b times 50. So b ends up being 0.6, so delta t equals 0.6 seconds. Miguel now drops another ball from the same height on the scale pan. This ball is the same mass as the first ball, but it's made of a harder material. That means it will spring back faster and have a bigger force on it, and have so it'll actually be a bigger force over a smaller time. Over a smaller delta t. So the sketch we would get will actually say that this force is, so we'll put 50 here, and we'll say that this is bigger than 50, and that delta t is less than 0.6. And I would even write here force in newtons and time in seconds, like that. Okay. So that is the solution to that particular problem right there. That's number 18. We'll take a look at number 19 in the next video.